Hello. So in the previous videos, we extensively studied the simultaneously move game, or it's also called the strategy game, right? But however, sometimes we could often see that the games are not played simultaneously by a lot of players, right? So it's sometimes one of the players moves first and the other moves later, right? So there is a sequential structure of the decision problems, right? So to capture this feature, and we introduce the extensive games with perfect information first, and later we'll discuss the another chapter for the extensive games with imperfect information. Okay, so the information, the perfect information here refers to the I will later formally define this. Okay, so it refers to the knowledge of the other player's moves. Okay, so now let's have some notes first to state our motivation here. Okay, so the main motivation is that because Nash equilibrium, the very general solution concept, Nash equilibrium is actually not satisfactory in the sort of the extensive games. Okay, because it just ignores the sequential structure of those decision problems, right? So Nash equilibrium it becomes unsatisfactory. Okay, in sequential decision problems. This is because that Nash equilibrium simply ignores the sequential structure of the decision problems. Okay, and later we'll use the formal propositions to prove that why we are saying so. Okay. All right. And later we'll use an alternative notation of it's called a new solution concept called subgame perfect equilibrium. Okay, so it's called subgame perfect equilibrium. Okay, so basically this new solution concept, subgame perfect equilibrium, or sometimes called SPE. Okay, so it where a player is required to reassess the plans as play proceeds. Okay, so essentially that's the intuition behind this new solution concept. Okay, and we will also discuss what is the sub game of a full game, right? Okay, so let's begin with the notation, with the formal definition for a extensive game with perfect information. Okay, but before that, let's have some definition on the perfect information. Okay, so let's first define extensive game. Okay, extensive game. So you can find those definitions on the textbook written by Osborne and Rubinstein, right? So the game theory textbook. Okay, so the extensive game is just a detailed description of the sequential structure of the decision problems encountered by the players in a strategic situation. Okay, simply it has a sequential structure. Okay, it has some structure of who moves first, who moves second, and so on, right? So it has those requirements. Okay, so a perfect information, it refers to that at some game, if each player, when making some decision, so this player is perfectly informed of all the events that have previously occurred. Okay, So when making decisions or making some choices or actions, right? A player is perfectly, so accurately informed of all the events that have previously occurred. Okay, so that's called a perfect information. Okay, so it's and later in the maybe two sections next, we'll introduce the imperfect information, and sometimes players they face this imperfect information and they do not know some of the previous histories and some of those events, right? But this is actually we need to pay some attention to this concept, because sometimes if as we read some papers, and sometimes people they refer to they just misuse this concept, right? And if we see that there is some state, some random variable, some state, okay, which is unknown to some people, but if the players they do not know the if they all those players they do not know this state, okay, so then actually there will be still a perfect information, right? So so here if some player knows the realization of some state, then that player has some private information, right? And then that move of that player becomes some and that leads to some information set for the other player, and that the other player has some imperfect information in this case, right? So just be careful of the definition of the perfect information, right? Okay, so that's basically that's a brief definition for the extensive game and perfect information. Okay, so let's have the formal definition for the extensive game with perfect information. So an extensive game with perfect information, it has the following components or ingredients. Okay, so the first, the set of players. Okay, so this is the same as before. And H refers to the history. So a set H of sequences, it could be finite or infinite, which satisfies the following properties. Okay, this is set N of players, set H of sequences. Okay, and it refers to the histories of the extensive for game. Okay, so the first requirement would be that the empty set is also in H. Okay, and secondly, so if AK, K from 1 up to capital K, so if this AK, a family of AKs in H, so this K might be infinite, okay? And L is less than K, okay? Then AK from 1 up to L is also in H, okay? Because the subset of that sort of subset, right? So like if longer history is in this game, then a subset of that longer history, a shorter of that would be still in the history, right? Okay. And if an infinite sequence k, from 1 to infinity satisfies ak k from 1 to L, which is h, for every positive integer L, then ak this sequence from 1 to infinity is also in H. Okay. So each member of H is a history. Okay. So H is just a set of all the histories. Okay. A history profile. Okay. So a set of histories. So each component of history is each component of a history. Okay. So that would be each component of the element in H, right? So it is an action taken by a player. Okay. So let's say H is in H. Okay. So this will be the history. This is the set of histories. Right. And what else? And each action, okay, in H, right? So this will be the action, okay, the elements of H. Okay, so a history, it could be the terminal history, right? So if all the players, they have finished their moves, then this history includes all those actions. All those the history includes all those actions taken by the player. So that would be a terminal history, right? So AK from k equals to 1 up to capital K H. So this is a history. That is that is terminal if it's infinite, or if there's no AK plus 1 such that AK from 1 up to K plus 1 is also in H. Okay, so that would mean that this up to K would be the terminal, right? So it ends this game. Okay. So the set of terminal histories is denoted using the capital Z. Okay, so that's still the second that's the second requirement for extensive game, right? That's the second ingredient. Okay, about the third component of that, okay, there's so many math notations, right? Okay, so the third component is some function P. Okay, so this is a function P. This is not a set, it's a function which assigns to each non-terminal history, okay, assigns to each non-terminal history. So it means that each member in H excluding Z, okay. So the history, but not the terminal, right? Assign that to assign to each. So P assign a member of N to that, right? To that non-terminal history, because So it means that after some history, then or in the beginning of the game, some player has to move. So this is essentially called denoted by this p function, right? So p simply assigns the node or the history to some player, means that this player, okay, well, you are going to play, right? So that's essentially what it is doing here. Okay. So p is the player function. Okay. So ph is function is just the player who takes an action after history h. Okay. So that's so this p is not pretty difficult to understand. Okay, so finally, the last component of the extensive game with perfect information would be that for each player I, a preference relation, right? So we always have the preference or the utilities. So we have this preference relation, preferred so weakly preferred too, right? On this Z, okay? So this is a preference relation on the terminal history, right? So because after the game finishes, then the players they could know that okay, each player likes which outcomes the best, right? So that's captured by this preference relation. Okay. Preference relation of player I. Okay. And sometimes it's also convenient to specify the structure of an extensive game without specifying players' preferences. So then we could refer to as a tuple of n, h, and p without the preference, right? Okay, but for the full notation, then we could always include that, right? Okay, so now let's have a example for illustrating the idea of the extensive game with perfect information. Okay. So let's just adapt the example from the textbook. Okay. So the initial node or the initial player is denoted by this circle without the by the empty circle here, right? So it simply denotes the null set or the empty set here because it has no history before. So let's say this is player 1 is going to move here. Okay. So this is simply a game where two people, to player 1 and 2, they're trying to follow some procedure to share two desirable, identical, indivisible objects. So basically like $2, okay, two $1 coin, okay, 2 coins. Okay, so player 1 could simply choose that player 1 takes 2 and leaves 0 to the other player, or takes 1 and gives 1, or takes 0 and give it to the other one. Okay. After that, then player 2 could choose yes or no. Okay. All right. So if yes, then gets 2 and 0. If no, then both gets 0, 0. So we have the dot here as well. Okay. And here is player 2 is also playing. Player 2 could choose yes or no. So if yes, then it goes like what player 1 did, right? So if no, then it's 0, 0. Okay, don't forget those dots. Player 2 could be yes or no, 0, 2, 0, 0, right? Okay, so player one proposes an allocation, and the other one, player two, chooses either accepts or rejects. Right. So in the event of rejection, no person receives either of those objects. But if yes, then the players they get the plan as the player one did. Right. Okay, so each person cares only about the number of the objects that each person could obtain, right? So this is a standard extensive game with perfect information. Okay, so player two could simply see what did player one act, right? All right. So now let's use the notation that we defined before and try to write that down. Okay. So that would be n h p function, right? And the preference. Okay. Let's do that by each component in of that. So n would be the set of 1 and 2, right? Okay. H actually has a lot of histories, right? So let's see. So the first must be the empty, right? Don't forget about that. So empty is also a history of the game. So it denotes the start of the game, right? Okay, and 2 0. Okay, so it's just that, right? So the left action from player one, or 1 1 or 0 2, right? Okay, and so those three actions could just be the history for this game. And after that, so after 2 0, then player 2 could play either Y or yes or no, right? So it means that 2 0, okay, 2 0 and Y together, okay, this is also history, right? And similarly, 2 0 N, okay, right? And also similarly 1 1 Y, right? 1 1 no, 0 2 Y, 0 2 N, right? Okay, that's a lot, right? So, and this also satisfies the requirement for the set H, right? As we mentioned before. So H includes an empty set, of course, and and all those longer histories includes its subset. So it includes its own subset history, right? The shorter ones. Okay. So that's H, right? How about P? Okay, so P for the beginning of the game should be player one. And okay. And P for any H which is not empty would be player two, right? Okay. And that's easy. All right. And how about the preference relation here? Okay, so the preference relation, okay, so for the player one first, so because those preferences are defined on the outcomes, which means that on the terminal histories, right? So we can just focus on those ones, right? So 2 0 Y, okay, so the first one, this has to be greater, or this has to be strictly preferred than the other one with no, right? Actually, that's something later, right? The next one should be 1, right? Because here's 2 and here's 1. So the next one would be 1 1 Y, right? Okay, all right. And all the others are pretty the same, right? Because all the others are zeros. So, okay, strictly preferred. Then all the others, we just write those down. Those could be just in any orders because we can just exchange the orders of those things, right? Those equivalent outcomes. Okay, so here is could be 0 to y because this is 0, and this has the same utility or the same preference for player 1 over 2 0 no, okay, and also the same as 1 1 no. And the same as 0 2 no, right? Okay, so for all those, just gives 0 to player 1, right? Okay. All right. So now, similarly, we could write down for player 2. Right. So player 2 prefers this, then that, then the others, right? Okay. So the first one would be 0 to y. Okay. Strictly preferred. Then 1 1 y. Okay. Then then all the others, right? Let's say 2 0 y. And the same as 0 2 no. Same as 1 1 no. Same as 2 0 no. Okay. Right? Okay, good. So now we are successively writing down the formal notation for extensive game with perfect information, right? And that's pretty long especially for this preference relation, right? Okay, good. All right, but so far, what we could analyze is simply still based on those actions, right? And since we have defined the actions are just elements in the histories, given some previous histories. But actually, because of those sequential structure of of this kind of game, right? So actually we could analyze those actions together, okay? So to put them together and consider it in another way, which is called strategies, okay? So basically, a strategy of a player in an extensive game is just a plan, or sometimes we often call that as a contingent plan, which specifies the action chosen by the player for every history after which it is this player's turn to move. Okay. So now let's formally define that. Okay. Strategies. Because sometimes the players, they need to move. For example, they might need to move twice, right? After two different timing, then they need to move again, right? So if we could analyze in aggregately, then that might lead us to some new social concept, right? Which is called the subgame perfect equilibrium. But that we'll define that later. Okay, so let's define strategies first. So a strategy, okay. So basically, the intuition for the strategy, okay. So in English, is that the strategy of player in this extensive game is just a contingent plan contingent plan which specifies the action chosen by a player. Okay. For what? For every history after this history, it is this player's turn to move. Okay, so that's the intuition for strategies. So how about the formal definition? Okay, so a strategy of a player I in an extensive game with perfect information, NHP preference. Okay, so a strategy is a function that assigns an action in AH after some history to each non-terminal history H, excluding the terminal, right? Now his non-terminal history. And there's a requirement for which this is player I's turn to move, right? So basically, a strategy is simply a function which assigns an action, right? In after some non-terminal history, and at this history is this player I's move, right? So that's essentially what we call as a strategy, right? So this notation of the strategy in this extensive game with perfect information depends only on the game form, right? So it doesn't depend on the utilities or the preference, right? Okay, so for example, in the previous example, right? So player one takes action on the after their initial history empty set, so that we could identify each of the strategies with one of the three possible actions that the player one could take after the history. So the strategy could be 2-0, 1-1, and 0-2, right? So player two takes the let's see the picture here. So player two takes the an action after each of those three histories from player one, right? And in each of those cases, the player two has two different possible actions, right? So then we could identify each of the strategies with a let's say a triple, okay. We could call it as A2, B2, C2, where those A2, B2, and C2 are just actions that player two chooses after the different histories. Okay. So the basic intuition or the interpretation of player two strategy, A2, B2, and C2 is that it is just a contingent plan. So if player one chooses 2-0, then player two chooses let's say A2. If player one chooses 1-1, then player two chooses B2, and if player one chooses 0-2, then player chooses C2, right? So that's essentially what's it called by the contingent plan, right? All right. So So we could have a node for that, right? So, for example, but maybe we could do that later, right? So when we have to do that, maybe we could have that example and the interpretations of the details later, right? We'll use that later. Okay. All right. So okay. So now let's define the outcome of a sequential game with perfect information, right? So we have the definition for outcome. Okay. So basically, it means that for each strategy profile, S, okay, for all the players, which becomes the profile, right? In the extensive game, NHP and the preference. Okay. So we define the outcome. Define the outcome of this profile S to be the terminal history. So the outcome is just the terminal history, right? That results when each player I follows the precepts of SI. Okay, so that means OS, this outcome, is it could be possibly infinite, is the history A1 up to A capital K terminal history, such that for K from 0 to capital K, we have this profile S P A1 up to AK, A1 up to AK is AK plus 1, right? Okay. And also in a strategy game, we could define a mixed strategy to be just the probability distribution over the set of pure strategies, right? Okay, so now we have those definitions, then we could refer to our familiar solution concept that we discussed previously, which was Nash equilibrium, right? And the reason that we could simply we could still have Nash equilibrium is that this extensive game could be simply transferred to a strategic game or simultaneous move game, because the reason is that those those players, they simply their actions could be regarded. So their strategies in the extensive game could be regarded as the actions in the simultaneous move game, right? So given that reason, then we could naturally to define the Nash equilibrium of the extensive game, right, with perfect information. Okay. So a Nash equilibrium of an extensive game with perfect information. So NHP preference. So an equilibrium is just a strategy profile. Okay. S star such that for every player I, we have the outcome of the strategy profile for the other players, and we have the we're pretty familiar with the notations for those, right? For the Nash equilibrium. So we have this gives a weakly higher preference or utilities, right? Other than, so compared, so this is weakly preferred, then the outcome given all the other players' strategies, then this player I strategy for some other deviations, right? For every strategy SI of player I, right? Okay, so that's one way of defining a Nash equilibrium of extensive game, right? So alternatively, we could also define a Nash equilibrium of extensive game gamma. Okay, so sometimes we use gamma. We often use that in extensive game. Gamma as a Nash equilibrium of the strategy game derived from gamma. Okay, defined as follows. Okay. Okay. So, or we can define a Nash equilibrium of an extensive game gamma as a Nash equilibrium of the strategic game derived from gamma, so as we just mentioned, right? So as those contingent plans, as their actions, so this could be transformed or derived into a simple strategic game, right? Defined as follows. Okay. So we have another definition. So the strategic game, or strategic form, not game, of the extensive with perfect information gamma okay is the strategic game and SI and the preference relation prime, a new one. Okay, so where for each player I, we have first Si is, okay. So recall that this thing should be the action profile that we see previously, right, in the strategy game, and this is the this is the preference relation in the strategy game, right? So Si should be the set of strategies of player I in gamma, okay? And second, this preference prime, this new one, is defined by S is strictly preferred prime to S prime if and only if the outcome of the strategy profile S is strictly preferred, then the outcome with some S prime for every S, right? So S is just the product of SS and all the S's, SS primes. Okay, so that completes sort of the transformation of the dynamic or an extensive game into a strategic static game, right? Okay, and that's quite useful. So we could use that later to show some interesting properties, right? All right. Okay. So that's the definition for the strategic form of a extensive game with perfect information, right? And we could also have a reduced strategic form of a extensive game, okay? So now let's have that definition. So let gamma to be the previous one, okay? Be an extensive game with perfect information. And let this N Si preference relation prime. So this would be its corresponding strategic form, okay? So for any I defines the strategies I define the strategies Si and S prime of player I to be equivalent if for each S minus I we have S minus I, Si is equivalent for player J to S minus I, Si prime for all J, okay? Then the reduced strategic form of gamma is the strategic game, so this would be a new one, Si prime and preference prime double prime, okay? Where for each I in N, each set S prime S single prime contains one member of each set of equivalent strategies in Si And this new preference relation is the preference ordering over the product of Sj prime induced by this single prime, right? Okay, so that's a definition for the reduced strategic form, okay? And just for us to know, right? But we might not give any related results for that, but just something that we could know for now, okay? All right, so in the next episode, we'll have some examples for those definitions, and later we'll also introduce the new solution concept called subgame perfect equilibrium.